you first write down the equation satisfied by V. So you subtract the two Euler equations. Well, I mean, there is one for U1, one for U2. You make the difference, and you find that the V will satisfy dTV plus P of U1 dot grad V plus V dot grad U2 equals 0. Right. And of course, divergence of U1 is divergence of U2 is 0. So divergence of V equals 0. Which means that the Lorentz projection of V is V itself. I mean, it's divergence free, so when we project onto divergence free fields, we do nothing. That's the equation satisfied by my V. And as we have seen, we can perform energy estimates, right? That's a basic tool. So we will do that on this equation for V. We multiply by V, and we integrate over RD. In the last lecture, it was a bit formal. I said we needed some smoothness, we needed some decay to make everything rigorous. But here, we are dealing with smooth solutions, so there is really no problem. So that's little remark. As U1, U2, and V, which is the difference, are smooth enough, one can check that all computations are rigorous. There is nothing tricky here because we have enough smoothness, enough decay. So what do we get when we do the energy estimates? We multiply the equation by V. We had seen yesterday that when we multiply this by V and integrate, we get the time derivative of 1/2 of the L2 norm of V. Right? And then we have two terms. So we have U1 dot grad V. This P is a symmetric operator, right? It's a projection. Orthogonal projection, I can put it on the other guy. And the same for the second term. And all of this should be 0. But I said PV is V, okay? So you can forget about this P here. Forget about it. And so here, what do we have? That's a computation we had performed last time. I will do it once more. U1 dot grad V times V. That's U1 dot gradient of V squared over 2. And when we integrate by part, divergence of U1 shows up, and it's 0. So this term is 0 here. And then you have to control that one. For that one, you don't have this nice cancellation. Okay? What you can say is that V dot grad U2 times V, you take the absolute value, you can bound it by the norm of gradient of U2 in L infinity times the norm of V in L2 squared. And again, here, we use that this guy is finite. Okay? And why is this guy finite? It's because of our choice of S. Okay? As S is greater than d over 2 plus 1, hs minus 1 embeds into L infinity. Okay? So I can control the gradient of U2 with L infinity by gradient of U2 with HS minus 1. And this will be less than constant times U2 in HS. So this will be finite for any time. So again, I use the regularity. And finally, I end up with d over dt. There is a 1/2 here. I have the nth norm squared of v, and this is less than some constant. Let me make it explicit. This is less than the L infinity norm of gradient of u2 times the L2 norm. Be careful, when I write things like this, that's L2 norm only in space. Only in space. Here, this is at some given time. Right? The L2 norm here is only in space. All integrals here are over RT. What happens here? I can integrate inside. And I take into account the fact that v at t equals 0 is 0, right? Because u1 and u2 were starting from the same initial data. So v at t equals 0 is 0. So v at time t will be less than a constant times integral from 0 to t of the norm of v of s ds. And so now you can invoke the Gromval inequality. Okay. That's for uniqueness. I think the difference between the two I estimate, and I can close some kind of Gromval inequality. So now let me show you existence of a local time solution. Again, I will focus on the Euler case. Okay, so this proof, again, is classical in this field. And we can say there are 3 steps. Step 1, consider the treatment of any PDE. That's a regularization procedure. Regularization. Which means that we do not want to solve directly the Euler equation. We will first consider some easier approximate equation. And so here, the approximation will be through frequency truncation. What do I mean by that? Definition. I take some maximum frequency capital N I denote by chi n of psi the characteristic function of minus nn to the v and what I will call chi n of d is the Fourier multiplier that's the operator defined by chi n of d applied to a function f. When I look at it in Fourier space, that's just multiplication by chi n of psi. So when I apply this kind of operator, what am I doing? I'm cutting frequencies. Okay? I go to the Fourier space and I only keep frequencies that are less than n. Okay? So with this kind of operator, with this kind of frequency truncation, there is a key point this chi n of d, well, it sends n2 to its range. Okay, so to chi n of d of n2. But in this range, you have only functions that have frequencies less than n. Okay? So this is included in any HS.